at Isaac Newton Institute. I think that it's time to introduce the first speaker for this morning session, and it's my pleasure to introduce Professor Wolfgang Dahmen from RWTH Aachen, Germany.
That's the past. I'm from South Carolina now.
Oh, okay. So you move, yeah. So recently joined South Carolina University. But the most important thing is that it's not a problem, because you are always the same researcher and professor. So your field of expertise are related with approximation theory and numerical analysis for partial differential equation. I would like to underline that Professor Dahmen got the Leibniz Prize in 2002, and in 2011 was invited to deliver also the Gauss lectureship. And between 2014 and 2017, he has been the chair of the Society for the Foundation of Computational Mathematics. So I would like to invite Professor Dahmen to join the stage for his talk.
This one. White noise. Thank you very much.
The title of his talk will be Parametric PDEs, Sparse Polynomial, or Roll Length Approximations.
Thank you very much. Okay, thank you very much. Yeah. Good morning, everybody. It's a great pleasure to be back here in the Newton Institute, but I noticed I did change my affiliation here, so I keep on forgetting these things, so sorry. Anyway, as you see, I'm going to report about joint work with Markus Bachmayr, who is actually here, and Albert Cohen from Paris. So let's have a brief look at the contents of what I would like to cover. So I will start with the model problem, and I will try to formulate some objective and questions that come sort of from our point of view, to explain why we are doing what and how. And then I will focus in on a generic adaptive algorithm, which happens actually to apply to a number of specifications, which I will then proceed to discuss. And there's always the question when you do kind of an adaptive method, there's of course the question, what does it really buy you? In what sense does it perform perhaps in a better way than something non-adaptive or something more straightforward? And so this has to do with the complexity analysis. But a complexity analysis is only possible, you can only say a method performs on a given problem in such and such a way if there is some structure of the solution sitting in the back. So in classical scenarios, this structure is usually described in terms of regularity or smoothness. So you can say if a function has so many bounded derivatives in that norm, then to achieve a certain accuracy in computation takes so many degrees, so many operations, or something like this. You can never say, you can never give any rate of convergence or any complexity estimate if you do not assume any kind of structure of the function. A generic function, it can be as slow as you wish. Now, the point in an adaptive method is that the method itself does not know this property. It finds it out by itself. So a complexity analysis for an adaptive method is important to point out the result we get is true if the target function has a certain property, but the method doesn't know that property. It will sort of realize this automatically. In fact, in an adaptive context, the method should be not subject to any condition, because any a priori assumption is something you may not able to verify, or that may not actually be true. So that is a very important distinction. So now in these cases of problems which come up in uncertainty quantification, most notably problems in very high dimensions, the classical regularity measures mean nothing. So usually the structure of the function is then described in terms of something else, like sparsity. Okay? So in this section 4, I will briefly hit on a certain points whose treatment in depth would take a lot more time, what we know beforehand about the typical structure of solutions to these problems. And they give benchmarks. And it will then, when it comes to the complexity of a scheme, it means to say, well, for such a structure, the scheme does such and such, does optimally or not optimally, and so on and so on. And again, the scheme doesn't know that structure, but the structure has to be given as a benchmark to measure things against. So that is the flavor. And this will be happening in this last section when I get to this point. You have to warn me a couple of minutes before, okay? So let's go to a model problem. See, we are talking about models. I'm fully aware of the fact that in the statistical community, a model has maybe a different meaning than in a numerical analysis community. Here is just a cartoon aiming at the following problem. Suppose you're walking on that surface here, and you are interested in exploring the ground underneath your feet. You don't see it, of course, but you could be interested in a porous media flow. So in order to do that, you would have to know the permeability of the material down here. It's just a cartoon. And then when you take the simplest mathematical model like a Darcy flow, you eventually end up with an equation for the pressure. And that equation takes this form. So that is the model. A PDE that describes a certain state of a physical process. That's the model, okay, in this particular talk. So what do you see here in this PDE? It's a divergence of a diffusion or permeability coefficient, and the gradient of U has to satisfy a certain law. The point here is that this permeability condition, that this permeability coefficient describes an entity of possible underground structures parameterized by some parameter y. So you could think of A of y, and we make this more specific, as a function of all possible configurations of structure underneath your feet. And in a typical inverse question, maybe after drilling some holes and measuring the pressure head in those holes, you are interested of finding the parameters that are responsible for that particular state. That's the inverse problem. But as usual, when you solve an inverse problem, it takes many forward solutions. In a typical optimization step, you say, make a descent method. And in each descent method, you have to evaluate the model for a new parameter y. So underlying is, of course, the need for a very fast computation of this for a given y. So, and in particular, in an inverse problem, you will have many y queries, and each time you have to come up with a PDE solution. So that's a very complex process. So therefore, our interest in doing this process very efficiently. But not only efficiently, because in the end you want to say, oh, that what I did is somehow reliable. I mean, that's the whole point of quantification of error. So that's the main goal here, to be able in the end to give you bounds for your quantification. Not bounds which are based on an a priori assumption, which is not validated. Bounds which are a posteriori certified. That's a big difference. So here's another problem which looks quite different, but ends up with a very similar equation, where you ask for the same thing. In this case, you ask for a conductivity field, which has the same kind of diffusion coefficient based on measurements from the outside. So here is now in mathematical terms the model in slightly more precise terms. So what we typically face is a family of PDEs. You are looking for a solution, but that family depends on a parameter. that parameter ranges over some parameter set. Very often in uncertainty quantification, that parameter set is high dimensional. So you don't have 2 parameters or 3, you may have 1,000 or maybe infinitely many in ideal terms. So as a result, your solution then becomes not only a function of x and maybe of spatial and maybe temporal variables, also a function of the parameter. And if you have infinitely many parameters, you have a function of infinitely many variables, which is slightly worrisome. Okay? And we'll see that under which circumstances there's a way to get across. So really, it's not, we are not talking about one single solution, we are talking about a manifold, the so-called solution manifold, which is the collection of all possible states that can be attained as solutions of this PDE when y varies, when the parameter varies. So that carves out like a manifold out in infinite dimensional space where the solutions live. And it's a hopefully very thin subset of infinite dimensional space, which is signified by the fact that each state is a solution of a PDE for a specific parameter. Okay. So now we go to exactly the type of problems which are just motivated with the porous media flow or the EIT. It's a diffusion problem, and we can view it as an operator equation, but the operator depends on a parameter. So this A is that diffusion operator. It depends on a parameter which varies over this set. So my general F has this form here, AY applied to U minus F. So this is just a residual. Okay, and so we assume for simplicity that the solution of this PDE has always homogeneous boundary conditions. It's really to make life a little technically simpler. So what is now A of Y? And a very frequently encountered representation of A of Y is like that. There is a nominal coefficient which is independent of the parameter, and then there is an expansion of spatially dependent functions weighted with the parameters. So when this could stem from a random field which you parameterize, like by a Cohen and Löw transformation. Then these would be the Cohen and Löw basis functions, typically. But it could take other forms. Polynomial chaos have this form. So basically, if your original problem was a random field sitting in here, you may view this as a parameterization of the random field, and then it becomes formally like a deterministic problem. But now, at the price that you have many parameters that describe the possible configurations of diffusion coefficients. So at this point, and for simplicity, again, the parameter set is a hypercube, and that dimension of the hypercube is that index set over which these J range, and it could be less than infinity, but it could be infinity, at least in ideal scenarios. When you have a general Fourier expansion of a function, it usually has infinitely many terms. So of course, nobody computes with infinitely many terms, but the question is, how many of them do you have to take into account if you want to say in the end, I have a certain accuracy? For instance, if you start from the beginning, I don't like to compute so much, I only take 5 terms into account, then you give a 16-digit accurate computation for 5 terms, and what do you have? A wrong model. Because you have truncated the model from the very beginning, and that may by far not what you really are up to. So this is an issue that will come up repeatedly. So just for the rest of this talk, the operator therefore has this form, has this expansion, coming from the expansion of the diffusion coefficient inside this operator. So it's a nominal operator which is independent of y, and a superposition of these operators, which are having, again, second order elliptic ones in this case, which are only spatially dependent at x. They only depend on x, on the spatial variable. So it's very classical how to go about such equations. You just look at the weak formulation, which you get by multiplying your equation with test functions. In this case, because of this form, you have this expansion with these test functions, and then you have to ask your question, well, what are the right test functions? in order to get a problem that I can really analytically manage. And that is very classical. So the forward problem will then require, given any y, compute the state corresponding to that parameter, which is the solution of that PDE for that specific parameter. And due to this weak formulation, you will be seeking for this solution in the Hilbert space H10. For a numerical analyst, this is the best known object you can ever think of. So it consists of those functions which have one derivative in L2. So one square integral derivative and have zero boundary conditions. And we abbreviate this by capital V. So this is in abstract terms now the problem. And you see it depends on y. It's a parameter dependent weak formulation. And now, of course, the first question again, is this a well-posed problem? Well, under the typical assumptions made in many papers is that if these coefficients, even as functions of y, remain between two positive bounds, bounded away from 0 and bounded above, then everything is wonderful. So this meeting is not, or this talk is not about, say, looking at degenerate elliptic PDEs, which would be an interesting topic by itself. But as far as the PDE is concerned, we take the classical situation here. Well, then the next step is now, instead of looking for a fixed y to the solution as a function of x, we actually look right away at the solution as a function of x and y. Because for each y you get another state. And the proper function space to look at is then this mysterious space L2YV. Wow, it's a Bachmayr space. It contains those functions which for each y, which takes the L2 norm in y, but it has values in that Hilbert space H10 or V. It is incidentally a tensor product space. So it's a tensor product of the space V, which has functions in x, only spatial variables, and functions in L2 over y. And this is this parameter set, this possibly infinite dimensional cube. And the norm is simply this. You take the norms of that is the V norm, that is the function norm with respect to the spatial variables. For each y, you take the square and integrate over y, and this gives the square norm of this tensor product space. So we now made a decision where to look for the solution. And under the given assumptions, this is a very justified decision. We need to do that in order to finally say something about errors in an approximate calculation. You have to fix the reference topology. And in this talk, we will be fixing at this. See, if Gianluigi, his preferable choice would perhaps be replacing the 2 here by infinity. That means you look at the worst case over the parameter set. Okay? Big difference, by the way, in high dimensions. Big difference in computation. Anyway, so let's go on. So now we look at another operator which takes this tensor product space already into its dual. And what is it defined by? Well, we take the parameter dependent weak formulations and simply integrate over y to integrate out the parameter. Now we have a problem which shows no direct reference to a single parameter. It's over the whole space, with the spatial variable sitting here and the parametric variable sitting here. And under the given circumstances, it's very classical to show that this operator, which is induced by this, so it takes this Hilbert space into its dual, is actually an isomorphism. That is, it is bounded and it is invertible, and the inverse is also bounded. And that means whenever you give data in that space, you get a unique solution in that space. Saying that this operator is an isomorphism is the same as saying this equation always has a unique solution and is stable. In other words, when you sort of shake the data a little bit, that solution also is going to change only a little bit. That is everything encapsulated in a jargon like, oh, that operator is an isomorphism. It gives you continuous dependence on on the data, which is of course a thing to do. So what has to be kept in mind is this operator now inherits from from the operator A this expansion. So you can also write this operator as a superposition of J-dependent operators given here. You remember that A of J was, so that AY was a superposition of those operators, and the same of course is true for the B with these components coming from the J. They are just obtained by multiplying by the parameters and integrating that out. And what is the challenge in inverting this operator? Which means when you know the forward simulation is the same as inverting this operator. You look for a field U of x and y that satisfies this weak problem. Now, what is the challenge is you basically have a problem in infinite dimensions. That U you are looking for in principle depends on x and infinite dimensional parameters. Of course, we will never compute it exactly. But the point is, when we compute it approximately, what is the deviation from the true ideal solution, which does depend on possibly infinitely many variables. And we would like to have a rigorous bound for the computation in the right reference topology, which is this one. Okay? So that's the challenge, the high dimensionality. So let me briefly recap what is known about this type of problems. So we are we're far not going into any detail, but this is the background, what is kind of known. There's a beautiful field of analysis around these kind of problems, and let me just point at some main things. So first of all, how do you expand this? The solution U will eventually, the solution U as a function of x and y is sitting in this Hilbert space, which is a tensor product of this parameter dependent space in L2 and functions in H10. And how do you expand? Are you going to represent this function? That's a basic decision you make at the beginning. And what has transpired from a lot of research is that a good expansion system is to use a polynomial expansion in the parametric variable. So as a function of the parameter, you think of this as a sequence in polynomials, Legendre polynomials. Because you are working in L2, you take an orthonormal basis for L2, and that's a natural thing. So formally, your solutions will have a form like this. There will be an expansion of Legendre polynomials, but for these Legendre polynomials, they have now multi-indices. The new, because they are tensor products of many. The y is a y1, y2, y infinity. So these are tensor product Legendre polynomials, and this is a univariate Legendre polynomial with index nu j. And these index sets are simply these multi-indices of possibly arbitrarily long support, but each support being finite at a given instant, so that it makes sense. So that's a basis for L2 over that infinite dimensional cube, and therefore you are entitled to talk about functions with this form. Now the coefficients are functions in x. They are sitting in this Hilbert space. They are functions in x. These are the coefficients of the Legendre polynomials. And of course, one question is, can we find these coefficients for these Legendre polynomials? That would be a representation of the forward simulation. And here are a beautiful body of results that starts off with the following observation. If the expansion coefficients in your diffusion field, this is the parametric representation of the diffusion coefficient. This is always the underlying problem. Divergence A of y grad u, that's the equation. And that is the diffusion field. And for that one, we have assumed this kind of expansion up there. This is our Ansatz, Cahunen-Löw, if you wish. And the first observation is if these basis functions decay properly, in other words, they are summable in some sense, then the same type of summability carries over to the coefficients in the solution. Okay? So this is in the data. This is in the data. The data are the diffusion coefficients here. This is an assumption on this. And what is this? Is a property of the solution to this equation. So that's very important. In other words, this ansatz, this justifies this ansatz to a great deal. And there are interesting consequences, like one is that the mapping that takes a given parameter into the solution is actually holomorphic. It's very smooth. And by the way, that's the reason why you can expect that an expansion like this is actually sparse. And in spite of the fact that you have maybe infinitely many variables, you may expect to have a manageable expansion here, that only a few of those terms are really important, and the rest you can actually cut away without making a quantifiable error. So that's this thing. Then in this theory you come up with a priori estimates for expansion systems. And you have even conclusions for approximation theories on decay of n-widths. N-widths are described, these are a sequence of numbers going to 0, and the quicker they go to 0, the thinner is the solution manifold. That is a measure for say, the thinness of a compact set in an infinite dimensional space. So a lot of things are known. And that have given rise to many numerical methods, notably sparse tensor product approximations, collocation, and things like this. But one common trait of these methods is they are based on a priori analysis. So typically they say if this and this is true, then you can expect this and this and this convergence rate. But what about error quantification? Because in many cases you don't know whether this and this is true, which entails this and this convergence rate. So here the point of view is completely different. Now we do not make these a priori assumptions. We are in this talk, and I'm not talking that down, it's very important to have this a priori theory, because otherwise, because it actually gives you this kind of benchmarks to compare to later. But here our interest is not to produce a certain convergence rate given assuming certain assumptions, but here it's a completely a posteriori point of view. In other words, we have the problem, we have an algorithm that computes, it stops, and it guarantees a certain accuracy. And that's my understanding of error quantification or uncertainty quantification in the result, right? You really want to be sure. Anyway, so now you may ask, well, let's revisit this. How do we get about this? In which way do we represent these functions as possibly infinitely many variables? And I would like to present three possible types, which we sort of put into a competition, in quotation marks, actually. And they are all possible based on approximation theoretic concepts. The first one is, we may look for approximations that are simply superpositions of a basis for the full tensor product space. So we can think of a basis for the space H10, which is V, in spatial variables, and a basis, the Legendre polynomials, for L2 over the parameter set. And we expand the solution, and of course the expansion coefficients are the unknowns which we would have to track. So we call this adaptive sparse polynomial approximation. Adaptive sparse polynomial approximation. So everything here, the expansion system is chosen before. These are the Legendre polynomials in Y, and these are basis functions in X. So they are chosen before, and all we are asking is, can we find a good approximate expansion by finding the coefficients in this a priori chosen basis? You could do something else. You could say, well, and this is more in the spirit of low rank and tensor approximation, you could say, well, this is a problem over a Hilbert space, over an L2 type Hilbert space. I can look for a Hilbert-Schmidt decomposition, which sort of gives me, for sure, the best low rank approximation. In other words, the smallest terms, the smallest number of terms for a given target accuracy in the Hilbert space norm, actually in this Frobenius norm type norm, so that the approximation is not with respect to a priori basis functions, but with respect to new functions that are separable and for instance correspond to the singular value decomposition of a matrix. So this would be the left, this would be the columns of the left orthogonal matrix in a singular value decomposition, and that for the right. And this would correspond to the singular values. And that means an approximation like that, if you were really able to find the Hilbert-Schmidt approximation, then these was, for a given accuracy, this would be sort of the smallest number of terms you need. But, so you can expect this is a much more compact, or it could be a more compact approximation than this one in terms of the number of terms here. Here it's n terms, here it's n terms. But, of course, the big difference is, here the basis system was known, here this has to be determined. In a way, that's a double nonlinear problem. You have to find these functions at the same time while evolving the approximation. So you may expect fewer terms in an approximation for a given target accuracy, but you're also paying a higher price because you have to find these good basis functions at the same time. Okay? And the third one I don't even dare to state. It is you go ahead and tensorize these functions even further, because these are still infinitely many variables in y, so you could think of replacing them again by higher order tensors, which are a completely separable representation in terms of the yj's. So I'm not detailing this because, no, it's too much. Anyway, so so these are our three types. I will comment those briefly on this one, but we will focus in more detail on these two. So what are the questions now? Well, is there among those three any best? Is there one which you should always take? Maybe that's our golden rule. We have now three competitors, and so which one would be good to use in a forward quantifiable simulation? Okay, natural question. Well, what about a posteriori certification? I mean, how do we? Not a lot is known about this in this problem setting, and I don't mean heuristic rules. I mean real rigorously founded results. Can this be achieved by intrusive methods or by non-intrusive methods? Of course, the practitioner would always prefer a non-intrusive method because he can recycle the code that's there. Okay? So, what is then the complexity? As I said before, in order to assess the complexity, there has to be some approximation theory which gives you an idea of what the regularity of the solutions typically is. Regularity in very vague, in very general terms, meaning sparsity. Okay, or approximability in general. Does in all this the type of the parametric expansion matter? So we made this ansatz for the expansion of this diffusion coefficient here. In terms of, say, a Carr-Huhn-Löw or similar, or polynomial chaos expansion, does it matter? It does, actually. And so what are the objectives? Develop a fully a posteriori controlled algorithmic template that actually can be specified to the three types. It's one and the same algorithm that can be specified to the three types: sparse polynomial, low rank, hierarchical tensors. Each of those is just a specification of the same algorithmic template. And above all, that I want to stress this because I see many papers and people justifiably worry about, oh, these big, when we do when we try to solve a linear system in this high dimensional case, we get humongous matrices. Are they actually sparse? Good, of course, good question. Here's a point: we never invert such matrices. Never, not at any stage. So we never invert a worry about the sparsity of a fixed discretization, because there will never be a fixed discretization. There will always be, depending on the state of a solution process, a adaptive current approximation, and in that one there's never an inversion of a linear system. It's only an application of an operator. That's a big difference. Now, and analyze convergence and complexity. Okay, here's the adaptive algorithm. The rule, the idea is easy, and in fact it's not new. The idea has been used in other contexts, and in these other contexts when people usually blame, why do you do these things on such an abstract level? Well, the thing is, you can use it later in other instances as well. So sometimes formulating things on an abstract level actually helps, right? So what is happening here? No, we have identified this operator equation, and we know that the operator from this Hilbert space into this Hilbert space is an isomorphism. That's analytically verified. Now, one idea is to choose a Riesz basis for this humongous Hilbert space. What is a Riesz basis? I will detail it later. It's an almost orthogonal basis. It's not quite an orthogonal basis. That may be practically prohibitive, but it is close to. Okay, now we have this basis for the full space, not giving away nothing. So no a priori truncation of anything. Well, then you can actually formulate this original weak formulation problem in this humongous Hilbert space as a well-conditioned system in a sequence space. This is the sequence of all, these are all sequences that are summable, that are square summable, and whose indices come from that tensor product. These are the spatial indices of a basis in this space, and these are the indices of a basis in this space. So that's an old idea. I mean, this is why people first transform an ODE into a linear ODE with constant coefficients by the Fourier transform, because you get an algebraic system. That's a very similar thing. This is only a more modern system to expand than the old Fourier system, but the idea is very, very same. But now you take advantage of the fact that this new system is mapping the same space into the same space. You see, that operator doesn't. It maps this space into another space because here's a dual. So it's not easy to formulate an iteration in that setting. You can formulate a fixed point iteration only if your operator takes something into the same space. So in the transformed version, that operator, this representation of that operator, takes the space into itself. Now you can formulate an iteration. And the fact that this is a well-conditioned problem will help us to say that this iteration actually converges with a guaranteed error reduction per step. And the numerical realization is then to mimic this ideal iteration by an adaptive approximation of each step within suitably chosen dynamic tolerances that guarantee convergence to the right thing and are accompanied by an a posteriori estimate each time. So here is now I'm going to comment about these points. So the first is the choice of that Riesz basis and the transformation into an equivalent system. So this is point 1, 2. And then the next I will comment on point 3, 4. So point 1, 2. So what is the background basis for that Hilbert space? Using that this is a tensor product space. Well, we first take, suppose for a simple domain, a Riesz basis in H10, and there are by now workable, well-known wavelet systems that do exactly this. And a Riesz basis means this: if you take an expansion in these bases and you measure the norm in that Hilbert space, it's equivalent to the L2 coefficient norm. So if there was an equality, then it would be an orthonormal basis. But we only require this to be equivalent uniformly with constants from above and below. That's called the Riesz basis. Then for the parametric factor, we have a convenient orthonormal basis. So there we don't even have to give an inch, but this is the Legendre basis. So as a result, taking a basis for the spatial variables, a basis for the parametric factor, you get a tensor product basis for the whole space. And that is easily seen to be actually a Riesz basis. If that was also an orthonormal basis, then this would be an orthonormal basis. But since this one factor is not orthonormal, it is only a Riesz basis. But this is perfectly enough. So what is the corresponding operator in data representation? No, we take the representation of our operator B with respect to that basis. In other words, we apply it to a basis function and test it by another basis function, and that gives a matrix. It's an infinite dimensional matrix. we don't even think of trying to compute it. Oh, okay. Gee. Oh my God, you see? I was trying to explain too well. Anyway, so maybe I jump to the results later in 3 minutes, and then I have 2 minutes for the rest. Okay. So that is let me continue showing that. And now we look at the particular form of this operator representation, and we make use of its special expansion form. That is a superposition of this. And at the end of the day, you find that this matrix operator representation is also an expansion in terms of tensor products of a spatial operator and of an operator that acts only on the parametric part. And this one is in this case due to the three-term recurrence relations of Legendre polynomials, actually bidiagonal. So this is very sparse. So in other words, when we look for the solution, so for the coefficient field of a solution in terms of this tensor product basis, then this is the same. The original problem is the same as solving this matrix problem. And the main point is, in this formulation, the norm of the solution vector is equivalent to the norm of the right-hand side, or the range, the norm in the range of the operator. That's the key, because then we can think of an iteration. And that iteration in the simplest form can look like this. We make a simple fixed point operation. You see, when un is the true solution, this is 0, and then it says u equals u. This is a trivial fixed point iteration. But the point is, we can choose a fixed damping parameter here to ensure that this contracts, and so that in every stage the error is reduced by a fixed constant factor. So now this cannot be computed. Neither can you apply this infinite matrix, nor can you apply it to a possibly infinite vector un. This is not possible. But the adaptivity in this scheme relies only on mimicking this ideal iteration in an adaptive way. And how this is done? Okay, so suppose we have a current approximation u bar n in any of the three formats, either hierarchical or sparse Legendre expansion or what you want. So then we update it to the next, and of course we have to approximate the application of B. And this indicates that this application will be done only within some target accuracy, called here eta. It depends on the stage. So when n grows, this will be tighter and tighter. Okay, now we get an approximation to this part. Then we have to approximate the infinitely many data, the load vector, which is also infinite in general. So this is this. But now we have screwed up the format. For instance, if this is a low rank form and we have done this, it will no longer be low rank, or the hierarchical tensor structure will be destroyed. So we have to bring it back to its structure. So this is what we call a recompression, going back into the tensor or low rank format. And then finally, if you go for the low rank approximation, the factors are in general have infinitely many expansion coefficients. So they have to be coarsened in order to get the best accuracy complexity measure. So there's another coarsening operation. And then one can choose these tolerances in such a way that this still converges to the exact solution. And in fact, one can show that this contracts at every stage with a possibly different row from the original one, but still less than 1. So that means after n of these steps, you would know how accurate you are, and that is your bound. But in order to execute it, you would need these kind of routines that apply the approximate evaluation of such an operator application, that approximate the right-hand side, that coarsen back, like in this case, a given expansion to keep only the fewest possible terms for a target accuracy, and that recompress in terms of a tensor format when you use a tensor format here. And then you can show that this scheme terminates after finitely many steps. I'm provided you can compute in floating point arithmetic accordingly, and satisfies your target accuracy, because you know that rho bar to the n eventually reaches epsilon. So the only question is, when you ask for the complexity, the only question is, what is the cost of these approximations? So the only question is, when you apply an operator adaptively, you have to do that in such a way that you achieve this target accuracy guaranteed by an a posteriori controlled bound, and what is the cost? And that will be the cost of the whole scheme. And here I have to shorten now. I originally planned to go through this, and I jump to the results. Okay, so how do you describe these results? Well, there's this notion of best n-term approximation error. In other words, if you think of this sparse expansion, we just have to activate the coefficients here, or find the best coefficients to make this approximation as good as possible with possibly few terms. That's the so-called, that creates a norm. If your function has the fact that these best n-term approximations go like n to the minus s for some s, then this is a finite expression, and it is kind of a quasi-norm. And so the results will be of that type. Whenever the solution belongs to such a space, that means to achieve a target accuracy epsilon, you simply put this arrow bound equal to epsilon and solve for n, then you know you can definitely do it with a number of terms which scales like epsilon to the minus 1 over s. There's no d here. As soon as you are in this class, then you get this. And well, the same thing for the ranks. Let me go to the result though. No, let me. So the main point is matrix compression. The main point is to analyze the adaptive application of our operator B. And in order to do that, there's a principle that was already used in wavelet analysis. For instance, this is a representation of a boundary interval operator, which is full, but which becomes quasi-sparse in this kind of wavelet expansion. And then under a certain property, under certain circumstances, you can cook up an adaptive application of the operator to a given input, using the information of the input and using a priori structural information of the operator, which makes this very efficient. And one of those results is, let me go to the main. I have to skip over this. So, and the main result for the sparse Legendre polynomial expansion is this. So this imitated ideal iteration yields our target our target accuracy epsilon always, without any conditions. If the solution belongs to a certain sparsity class and the operator doesn't know it, then we can prove that the result scales in this optimal way. In other words, this is a finitely supported solution vector, and its support scales in the optimal way, epsilon to the minus 1 over s. And the number of operations needed to compute this scales in the optimal way, epsilon to the minus num over s. So it's actually linear in the size of the solution. And at no term there was an inversion of a big system. It's only the adaptive application of an operator. Okay, so for low rank we have a similar result. The specification of the same algorithm to low rank does the same. It achieves the target accuracy, and now the ranks scale in the optimal way. Now the ranks scale in the optimal way. I'm done. And but in this case you compute the factor functions, and these factor functions have finite expansions, and this is a measure for their complexity, and that scales in the optimal way depending on the parametric and on the spatial variable. Only in the computational cost for the low rank case, you have an optimal scaling here. There's this epsilon to the minus 1 over si, spatial parametric, that's expected, but you have a square factor of the cost in addition. Why is that? Because along the way you have to compute singular value decomposition. And these cost. And that is the additional quadratic cost of computing the singular value decomposition. And that is, I think, unavoidable. And okay, maybe that's for questions. I stop here. Yeah.
I've answered a couple of questions from the audience.
Well, the still question is what is best, right? And I claim it's hidden in those graphs. That's unfair for me, I know. Yeah.
I had a question about your algorithm. I think it was on slide 16. When you say things like you never have to invert a matrix, it's like magic, right?
No.
But if you're doing
If you do a fixed point iteration, you never invert a matrix.
I understand. What I'm saying is, in your algorithm, you had some parameters. I don't know if it was omega or rho.
Yeah.
As a user, one has to pick those things.
Right. Good question.
Highly
question.
influence the convergence. So
Yes.
how would I know how to pick those? Right.
That's the a priori analysis on your field. They depend on when you go to the first slide. I was saying that the coefficient field stays between little r and capital R, and it comes from those because these are Poincaré estimate coefficients and coercivity of the elliptic equation. They come from
Is
this.
there only a priori information about
There is a priori information.
input data that you need, or about the solution?
No. Input data. Yes, exactly. Not about the solution. There's no assumption on the solution. But that was, I should have pointed this out. You're right.
So, from the statistical side, I mean, there's a lot of work on sparsity, different definitions of sparsity for high-dimensional data. In fact, there's a parallel work track
Absolutely.
where they're doing lots of everything. So, the definition of sparsity in this work, can you give us a very short
Okay.
paragraph about what your sparsity means?
Yes. Okay. It says sparsity means like to achieve a certain accuracy epsilon. I try to approximate the Hilbert-Schmidt decomposition of the solution field, and in my approximation, I pick, say, for epsilon accuracy, I have n of epsilon terms, like a rank n of epsilon approximation. And sparsity means very sparse would be there are only very low rank. There are only very few terms you need in order to get an accuracy, but it's not a fixed number. It's always relative to the accuracy. And I show that the sparsity achieved here is minimal, because that is what the best ideal version would do. And the same in the Legendre expansion. I need a certain minimal number of terms to achieve a given accuracy tolerance. And I prove that the number of terms that are generated by this algorithm stays proportional to this. In the worst case, over the whole class. I mean, you could hit it.
So it's the rate of approximation versus the rate of the number of terms you need to get that approximation.
Absolutely. Exactly. And even classical results could be rephrased like this, because in classical results on approximation in low dimensions, there's an approximation theory that gives an equivalence between smoothness, regularity of PDEs, and this, I mean, centuries of research of regularity of PDEs, in terms of approximating them at a certain rate. So this is just an extension to high dimensions due to the fact that smoothness in the classical sense doesn't mean much in high dimensions. Right? But due to the curse of dimensionality, when you do one subdivision in a 100-dimensional cube, you have 2 to the 100 children. And regularity is an isotropic measure that diffuses in all directions simultaneously. So that is the classical regularity is immediately subject to the curse of dimensionality. You have to probe into too many directions to say something.
Yes, I mean, I have the impression that the key for the success is the respaces.
Yes,
That's
true.
what gives you everything.
It's true.
Now, for the small
Well, gives you a good edge. You have to do a lot afterwards. But
yeah, but for this model problem, you know perfectly well how to choose your respaces because it's H10.
yeah. Oh, I can give you a library of wavelet bases that
How
do that.
difficult would you rate would it be to generalize this to any application problem? I mean, is the first step in any application to first think about what would be corresponding almost
Well, okay.
or
Yes.
can you get
Okay.
get around this and do it?
Very good question.
Talks?
Here's the answer. If you're dealing with a problem that has a symmetric variational formulation, in other words, you cook it up in a weak formulation where the test space is the same as the trial space. So you look for a solution in one space H and you test also by H. That's what I call a symmetric variational formulation. If your problem allows this formulation and gives you an isomorphism in this formulation, then you can do that. Maybe with more difficulty in coming up with the good respaces, but essentially this is a major thing. But if your problem does not allow you to do that, for instance, a strongly convection-dominated problem, then your test space, in order to get this isomorphism property independent of that relation between convection and diffusion, then you need to take another test metric. And then this becomes more involved. And in particular, when the test metric depends on the parameter. So then you have to do something else. But by the way, you can do very similar ideas on an abstract level, not using directly explicit basis, but using what I call stable variational formulations. Okay, but that is true. For this diffusive problem, it's a symmetric formulation, and then you can do that.
I would like to thank again Professor Dahmen for this.